Okay, thank you. To introduce Eduard Feireisl, we call the Professor Diego. So, Diego, introduce now the Professor Eduard, please.
Okay, so thank you very much, Mauro, for the opportunity to introduce Professor Eduard Feireisl. Professor Eduardo is a Czech mathematician. He received his PhD in 1986 from the Institute of Mathematics of the Czechoslovak Academy of Science, and now he's a professor there. No, and Professor Eduard is he's received many prizes recognizing his scientific career. And his main topic is PDEs, infinite dimensional dynamical system, a mathematical problem of hydrodynamics. And today, Professor Eduard is going to talk about analysis of open fluids system with uncertainty data. So, Professor, thank you very much for accepting our invitation. And you can start when you want, in Spanish or English, as you prefer.
I would prefer in Czech, if you don't mind.
Sorry.
Okay, thank you very much for this invitation. Yeah, I'm really happy. I mean, I speak English because I think there are also some people who listen to the talk and they don't speak Spanish. So I think it's better to speak English. It's more universal. I would like to thank you for the invitation. I hope I have a little bit more time than originally, because I should finish according to the original schedule in 15 minutes. So I hope you give me a little bit more time. I will still try not to be too long. So I'll speak about analysis of open fluid systems with uncertain data. So this is more like applied mathematics that Juan Luis was talking about. This is more applied than maybe a Laplacian operator or fractional Laplacian. But there will be still some analysis. But in this business, we also need to compute something. So I will also present some application to the numerical analysis of the problem, because unfortunately, finding explicit solutions to my system of equations is impossible, only in some, maybe in some special cases. So this is a joint work with my postdoc from Prague, Danica Basaric, with my colleague from Mainz, Maria Lukáčová, who is mainly also responsible for the numerical part of the talk, and also Hanna Mizerová from Bratislava. Okay, so let me start with the equations. I hope you can see the full screen as I can see it, because sometimes people don't see it completely. Just let me know if you don't see something. This is my problem. So that's a model of a compressible viscous heat conducting fluid. And although it looks like very complicated, I must assure you that this is really the simplest possible model of this situation, because I have only 3 equations. So maybe for people who are not so familiar with this model, let me explain the meaning of the equations. The first one is just mathematical formulation of the mass conservation principle. So there are several unknowns in the problem. There is rho, which is the fluid density, u, which is the fluid velocity, and theta, which is the fluid temperature. And so the whole system is about these 3 variables, and the first equation expresses the conservation of mass. So as you can see, this is not really a very nice system of equations, because it's of mixed type. For instance, the first equation is a kind of transport equation for the density. There is no diffusion here, so there is no regularizing effect absolutely at the level of density for the fluid. So this is the first problem, and actually this is one of the main mathematical issues that you have to face when you want to develop some theory for this problem. Okay, so, and in particular, you also have noticed that the problem is non-linear, and I would say it's strongly non-linear, although I know that some people don't like to use the word strongly because there is no exact definition. Okay, so that's the first equation, is conservation of mass. The second equation is Newton's second law, or momentum balance. Somebody mentioned Navier-Stokes system. If you are familiar with the Navier-Stokes equations, And you look at the second equation. I mean, Navier-Stokes system, usually people, when they speak about Navier-Stokes, they mean what is called incompressible Navier-Stokes equations. In this system, you take just the density to be 1, and the function which is here and which is called pressure, you just take it as an unknown. And here you take just Laplacian of u, and you will get the incompressible Navier-Stokes. So in my situation, it's a little bit more complicated because that's compressible system. So the density intervenes and also the temperature. And this is the viscous stress. So the fluid is supposed to be viscous, so it's a real fluid. And the viscous stress is this funny form, which is the so-called Newton's rheological law. So that's the simplest possible expression for viscosity you can think about, because it is actually a linear function of the velocity gradient. And it's usually split in 2 parts. The first part is called shear viscosity, which is a kind of deviatoric stress tensor. And the second one, which is just diagonal stress, is called bulk viscosity. And there are 2 coefficients of viscosity, and I will assume that the first one at least is always positive. The fluid is really viscous. And the last term in the second equation represents the gravitational force which acts on the fluid. So G is a given potential, and this is a gravitational force. Actually, it's the only volume. Well, in this system, people used to add a lot of other volume forces. However, I think this is the only reasonable volume force that can act on the fluid. And I would like to speak about the complete system, which means I would like to take all principles of thermodynamics into account. So I have to supplement this problem also by some kind of energy equation. Here, I write it in the form of internal energy balance, or if you want the heat equation, which is this one. And actually, you might be surprised, but there was already the equation we have seen in the talk by Juan Luis in a very simple form, because if you look at Q, which is the heat flux, I assume that it is given by Fourier law. So I assume there is a constant, and this constant multiplies gradient of theta with minus sign, which roughly speaking means that's also mathematical formulation of the second law of thermodynamics. I mean, the heat can only fly from places where the temperature is higher to places where the temperature is lower. And well, the expression here is the so-called internal energy, but in the simplest case, that we will see on the next slide, this internal energy is just proportional to the temperature. And so what we can see here is the partial derivative of the temperature minus Laplacian of the temperature. So that's exactly the heat equation we have seen in the first talk. Here it's a little bit more complicated because there are terms on the right-hand side, in particular the first one, which is due to viscosity of the fluid, which somehow expresses the heat which is being produced by the fact that the fluid is viscous and several parts of it exert some friction, and this is demonstrated by developing of heat. And this process, unfortunately, is irreversible, which means that this system, unlike what's sometimes called a hyperbolic system, is not reversible in time. I mean, it goes only in one direction. The mechanical energy is always transformed into heat. So this is my problem. This is the system of equations, and I would like to speak about open systems. And so I will have to supplement my system by some boundary conditions. In the previous talk, we have seen that the boundary conditions, sometimes they are being ignored by mathematicians because the problem is much nicer. And you have, I would say, broader spectrum of techniques that you can use if the problem is posed on the whole space without any boundary conditions. However, in fluid mechanics, if you want to see something interesting, you should introduce the boundary conditions. So maybe before I speak about thermodynamics, let me tell you something about the boundary conditions. I assume that my space, my physical space, is the domain Q, which is a bounded domain, but can be unbounded, as the case may be, but I will consider only bounded domains. I will assume that this physical space has impermeable boundary, which means that the direction of the velocity on the boundary is always tangential to the boundary, which means the normal component of the velocity is always zero. Now you have several possibilities how to choose your boundary conditions. The first one is these are the kinematic boundary conditions somehow related to the motion of the fluid. The first one tells you that there is a complete slip, which means that basically there is no adherence of the fluid to the boundary. The only condition is impermeability, so the fluid doesn't flow through. However, it moves freely along the boundary. Sometimes that's called complete slip condition. It's not very physical because what is being observed is really that somehow the fluid sticks to the boundary. And so this is expressed by the second condition. They cannot be imposed at the same time. So they can be imposed on different parts of the boundary. And this one is called no slip condition or adherence condition, which means that actually the tangential velocity of the fluid, which I express by the product with the external normal, is just given by some velocity field UB. And in most of the cases, people assume that this UB is equal to 0, and the resulting kind of boundary condition is then called no slip boundary condition. So the fluid completely adheres to the boundary, which is actually more physical than the first one. Now you have to impose also the boundary conditions for the temperature. So the simplest one is the Dirichlet type, where you assume that the temperature is just given on the boundary. So it's a given function. In some cases, it's also you can also prescribe the heat flux on the boundary. And the simplest possible way how to prescribe the heat flux is that you just say that the heat flux of the boundary is equal to 0. So which means that there is no flow of the heat through the boundary, and then the fluid is basically thermally isolated. And so these functions like UB and theta B, they will be my data. Later on, I will speak about problems with data, where the data are kind of uncertain quantities. They are not known exactly, so they are known with certain probability, which will convert my problem in a kind of parameterized system of equations, or if you want, a random system of equations. Before I come to that, I should go to the second slide because there are some other conditions I would like to discuss. The first one is that actually I assume also the second law of thermodynamics, which is usually expressed in the form by Gibbs' law. Gibbs' law tells you that actually if you take the internal energy of the fluid, the pressure, and compute the differentials and divide by the temperature, you will get another differential, which is a differential of a new function. And this new function is usually called entropy. And if you go back to the set equation on the previous slide, you will write, you can derive the so-called entropy balance equation, which is at the level of smooth solutions equivalent to the last equation on the first slide. And it can be written in this form. As you see on the left-hand side, there is something you would like to call conservation law. However, on the right-hand side, there is a term which is non-negative, and this is the entropy production. And this term is responsible for the increase the entropy. So, okay, mathematicians sometimes like to have entropies that are decreasing. In my case, I have the physical entropy, which is an increasing function of time. So the entropy is always produced. That's the second law of thermodynamics. I assume more physical principles. I assume thermodynamic stability condition, which is actually automatically satisfied in my when I specify my equation of state. It basically tells you that if you take the total energy of the system, which is this one, is the sum of the kinetic energy plus the sum of the internal energy, and you express the total energy as a function of new variables, actually of the momentum, which is rho times u, rho, and S, which is the total entropy, which is rho times small s, then this function is actually strictly convex. I mean, that's my assumption. And that's sometimes called thermodynamic stability condition, and it plays a crucial role in the analysis. Well, to be specific, I assume the perfect gas law or Boyle-Mariotte law, which is the most popular equation of state. So assume that the pressure is actually given as a product of rho times the temperature, and the internal energy, as I promised, is only proportional to the temperature by some positive constant CV. And so accordingly, the entropy is given by this formula. I mean, you can compute it from this equation. And so this is my problem together with the boundary conditions. Now, I should prescribe also the initial state of the system, which is given by these three functions. I prescribe the density at the initial time, say 0, the temperature. I assume that both are strictly positive because that's physical. I mean, recently you can find in the literature some papers where people study also problem with non-negative density, which means the density could be 0, and they call it problems with vacuum. I would like to say this is completely incorrect in this context, because the model itself is not a model of a fluid with vacuum. So one should not really impose 0 density as a kind of data. The same with temperature. The temperature in my system is the absolute temperature. The temperature should be positive, so the initial temperature in particular should be positive. And you have to prescribe some compatibility conditions. Now, what you can say about the existence of solutions, I'm not so ambitious to give you some formula. I mean, like Juan Luis showed us some nice formulae, how you can solve the heat equation. I mean, explicitly given some kernels. Here, you don't expect anything like that. You would be happy to say that the solution exists. I must say the situation is very bad from this point of view, because as you know, and it has also been mentioned, in the business, these are nonlinear equations. So you don't really expect to get smooth solutions because of possibility of the blow up. And unfortunately, very recently, there were really explicit examples of blow up of solutions, not for this particular problem, but for some related systems, say for the barotropic Navier-Stokes. And so if you think in terms of smooth solutions, you must confine yourself to some short time interval. If you think in terms of weak solutions, you may hope to get weak solutions that are defined globally in time. However, for this particular choice of state equations, in particular for the gas law of the type Boyle-Mariotte, as far as I know, to the best of my knowledge, there is no result about existence whatever of global weak solutions. But in my talk, I will be happy with new solutions, as you will see, because I would like to speak about uncertain data. And so let me remind you what is known about the existence of smooth solutions. Well, if you assume that your initial data are sufficiently regular, which sufficiently regular is being expressed in terms of Sobolev norms. So say if these are Sobolev spaces, Juan Luis called them H2 or Jacques Lyons, I call them WK, which are more general, in the sense that I can also speak about W2P and so on spaces. Well, so I assume that I have 3 derivatives which are basically square integrable for the initial data. If you don't like to work with Sobolev spaces, you just assume that they are 3 times continuously differentiable. And then Vali and Vali-Zarechkovsky in 86, and I would say independently also Kawashima Shizuta 88, and maybe some other people prove there exists a local solution of the problem. So, which means there is a short time interval, the solution exists on a maximal time interval, and after that, we don't know. And it's not even known if this interval is finite or not, meaning if there is a blow up or not. But there is no result about extension of the solution in the form of weak solution or whatever. Cho and Kim somehow a little bit relaxed these conditions in 2006, so they allow for, less regular functions. Unfortunately, the result holds only for the case when the boundary velocity is 0 and you prescribe the no-flux boundary condition. So in particular, if you are interested in Dirichlet boundary conditions for the temperature, which is relevant in some physical applications like a Rayleigh-Bénard convection problem, then this result is not really applicable. There is a nice, more recent result by Matthias Cochotte, where he works in what is called LP framework. He is using the technique of the so-called maximal regularity estimates, and he established existence in the LP spaces of this type. So he needs a little bit less regularity than he with respect to derivatives, but he needs more integrability because P is bigger than 3. And he can also prove the existence of local solutions. It's a nice result, and I will actually use this result for the formulation of in the future of some of the theorems I will mention in the future, because this result is maybe the most elegant and also maybe the most general. And also this result applies to inhomogeneous boundary conditions. So this is also important for me. So this is what we know about the existence for the initial value problem. And now I would like to say something about solvability of this problem when the data are not known specifically, but they are actually random in the sense that they are given with certain probability. I'm not going to do stochastic equations. I just assume that I'm not completely certain about the shape of the data, and I allow the data to be a little bit imprecise. And I would like to analyze the situation. In particular, I would like to prove some convergence of some numerical approximations of this problem. And it looks like this is a purely like computational task. However, I would like to show something. I would like also to say something about convergence of these numerical of the numerical solutions. And in a way, it turns out that analysis is very useful. And in particular, I will use results which are known conditional regularity. And they goes in line with the celebrated John Nash conjecture. Nash was, by the way, one of the first who proved results of this type for nonlinear problems. And what he conjectured in the context of the system of Navier-Stokes Fourier system is that, well, maybe the solution may blow up, but as soon as you control certain quantities, in particular, if you control the density or the temperature in some L infinity norm, say bounded norm, then the singularities will not appear. And indeed, this conjecture is true. I mean, there is a long list of results in this context. And let me mention the last one. Unfortunately, the last result covers only the case when the heat flux, again, is zero on the boundary and when the velocity prescribed on the boundary is zero. Again, this is not so much interested in applications where we would like to have also the temperature to be prescribed on the boundary or maybe even the velocity. And the result tells you the following. So the solution, the strong solution exists always on a maximal time interval, T max, when the norm in the strong topology and when the high order norm in which the data live blows up. Suppose that you can control only the supremum. I mean, rho and theta are always bounded below. So this means that you basically control the amplitude. So you suppose that on some time interval, you can show that the density and the temperature are bounded. Only this. Then the T max, the maximum time interval, must be bigger than the interval on which you control the density. So the solution cannot blow up. In other words, if the solution blows up, it must be in the L infinity norm of rho and theta. And this is an interesting result. It's a complete solution of, I mean, it agrees completely with the conjecture of Nash. And later I will show you how this can be applied in numerical analysis. But as I said, in numerics, we would like to solve more complex problems. In particular, we would like to assume that the boundary velocity is non-trivial. Well, we just assume that it is tangential to the boundary. And also, we would like to assume that the temperature on the boundary is given. And we could prove a similar result recently, where you have to add something more in this condition. Not only that you have to make sure that you control the density and the temperature, but you have also to control the amplitude of the velocity. And if you control these three things, then T max must be bigger than T, which means if you make sure that these three things are bounded, then the solution cannot blow up. And again, later on, I will show you how this can be applied in the analysis, in the numerical analysis, or in the analysis of convergence of numerical schemes. So this is the first mathematical result I will need, conditional regularity. Let me introduce the data, because I would like to speak about the data. So let me introduce the data space. It is convenient because I would like to have temperature, for instance, which is also prescribed on the boundary, and also initially to express the boundary data as a restriction on some function theta d, like data, which is actually defined at any time. Well, for convenience, I put infinity here. Of course, I don't have to have it defined on 0 plus infinity, but only on the time interval where I want to study the problem. However, it's more convenient to assume that the data are defined on the whole on the whole timeline. And I assume that this function enjoys certain regularity. In particular, I go in line with Cochotte's result. So I assume this regularity and assume that my initial and boundary data are given by the restriction of this function to the boundary and to the initial time. I do the same with the velocity, and I introduce the data space, which is actually the space of all rows. The row is not need not be given in this way because row is not prescribed on the boundary. So I just take row D to have the same notation, and I take it the initial value, and I assume that the initial value is positive. And so my data space consists of theta D, UD, and rho D that do satisfy also the relevant compatibility conditions. And I introduce the topology on the data space, which is this one, which is actually the norm of these functions in these spaces plus the norm of 1 over rho d and 1 over theta d, that because theta d and rho d should be somehow should be positive, so I have to control them also from below, which is represented by this norm. Well, so the space D, there's a space of data xd endowed with this well, kind of norm is actually a metric space. If you think about it, this is a norm of the 1 over rho, but if you take it as a function defined on rho d, d endowed with that is actually a metric space. And so I have a metric space. You can also show it's separable, so it's a perfect candidate for being used in the stochastic business, because working as measures on abstract spaces, we know that most of the theorem is stated on the so-called Polish spaces, which are complete metric and separable spaces. Okay, now the solutions we live in the trajectory space. So for each data, I have a solution which is defined up to the maximal time interval. It's actually defined uniquely by the data. The only drawback of this may be that this maximal time interval can be short. So actually, this maximal time interval depends on the data. And I will show you the second result that we could prove. So the solution lives in this space, which is actually given by Cochotte's result. You can also consider another space of strong solutions, which is given by solutions by the class of Baliza-Jączkowski or by the class of high order derivatives class that was introduced by Kawashima. But I will, for explicit, for specific, to be specific, I will consider this class of solutions. Now there is a second result which tells you that well, this maximal time interval is actually a lower semi-continuous function of the data. If I take the sequence of data, the n, which converges in my data space, in the topology, the data space to another data, xd, theta d, ud, then actually in of this maximum existence interval must be bigger than the existence interval of the limit. And the solutions themselves converge for any t which is below this maximum time interval to the solution, to the limit solution which corresponds to this data. So this is a kind of stability module of the maximum time interval. To the best of my knowledge, this result is also kind of new, although maybe some people would consider this result a little bit obvious. However, I have never seen it published, so we just wrote it down. And so let me summarize what we know analytically before I pass to the probabilistic part. To the random part, let me summarize what we know from the analysis point of view. So we know that for any data in my data space, there is a unique solution, which is a classical solution of the problem. I will not bother you with any weak solutions in my talk, which exists on a maximal interval 0 T max, where T max is always positive. The mapping which assigns to each data the maximal existence interval is lower semi-continuous, and we have stability, which means that if Dn converges to D, for each t which is less than equal than t max of the limit solution, I have convergence in the trajectory space. Stronger. This is what we get through. In addition, we have conditional regularity result that I mentioned, which can be stated in this form. It's a kind of a priori estimates, which means if I know the norm of the data, if I know capital T on which I consider my problem, and if I know the supremum of these three quantities, I can also bound the norm in the higher order spaces of the solution. So this is basically the conditional regularity. In other words, if this is controlled, this is controlled. And so this is everything what I will need from analysis. Okay, problems with uncertain data. The data may be uncertain in the sense that it's a sample of something, of some measurements, and so we are not really sure what is the correct what is the correct value. They can be uncertain simply because they are not available, and we only kind of estimate what they could be. And so mathematically, if you want to deal with uncertain data, I don't like to say in this context random, because it's rather uncertain. I mean, they are not really random, they are just uncertain because we don't know exactly what they are. And so, so the data, in order to express it mathematically, I need a probability space. So I take the standard measurable space. So it's a space which consists, it's a space of events, omega. There is a set of sigma algebra of measurable sets. If it's a topological space, I assume that it's also Borel measurable, and P is a complete probability measure. Now, all solutions now, all the data will be considered as random variables. In particular, they will be functions which for each omega in my omega space, I will have a data, and I will have the associated quantities like the solution. So now I take the data. If the data is a random variable, then the maximal time interval, because it's a lower semi-continuous function of D, so in particular, it's a Borel measurable function, so it's also a random variable. And also the mapping, which assigns to D the solution on the maximum time interval, is a random variable because it's actually a continuous mapping. And so I will consider something what is called statistical solution, which is nothing other. You can see it either as a measure which is sitting on the trajectory space and almost surely sits on solutions of the problem, or you can see it as kind of random variable which assigns to each omega the solution which is associated to the specific data. So the data is a random variable, and to each data I have a solution. So also the solution itself is a random variable living in the trajectory space. This is the strong sense. In the weak sense, stochastically, sometimes people consider the problem in the weak sense, which means that instead of considering specific random variables, you just consider their distribution, which is called law. So you are no longer interested about specific value for each omega, how the solution looks like. You are just interested what is the probability that your solution will live in some part of your phase space, which in my case is this space given by the regularity class for the strong solution. And so, and this distribution tells you basically everything about the behavior of the system from the stochastic point of view. And so this is the so-called weak sense, in which instead of taking specific solutions, you just consider their distribution. Okay, what is now my problem? My problem now is take random data. They will converge in certain sense, and I would like to say that the solutions converge as well. And so I will proceed by in several steps. I mean, and I will end with some application to numerical approximations. So the first example is kind of trivial, and actually when people think about this problem, they always think that it works this way. Assume that you have a sequence of data which converges to D, but now since they are functions of omega, they are random variables, assume that this convergence takes place almost surely, which means for almost in probability, instead of saying almost everywhere, you say almost surely. So for almost any omega in your probability space of capital omega, this convergence takes place in the data space XD. Right? Well, then the simple conclusion is, since the solutions are unique, that if you take the corresponding solution, they will converge in the space of trajectories for any t which is less than t max d, which is also a random variable, as we know, and the convergence will be almost surely. But that's immediate. And it's a kind of obvious statement, right? But the situation could become more complex. For instance, first, I can be interested only in the weak stability problem. Instead of considering my random data as a random variable, I will only consider that distribution, which is the law. It's a distribution of the data on my data space. So it's a probability measure now, which is sitting on the data space. And I will assume that I have a sequence of these probability measures which converges to some limit. And the convergence is in the space of probability measures, which is called narrow convergence, or if you want, B convergence in the space of probability measures. It basically means that that the measures converge for any continuous function. The integral over the measure converges for any continuous function. This is called narrow convergence. And I assume that I have data of this form. So I don't really know what the data are. I know only something about the law, about the distribution. And now I would like to say something about the law or distribution of the corresponding solutions. That's a little bit less trivial because we cannot use this straightforward argument like convergence almost surely, etc. But we can use some tools from probability theory, which is sometimes called compactness in probability or compactness tools in the probability theory. The first one is the so-called Skorokhod representation theorem, which actually makes it possible to pass from laws of some random variables to new sequence of random variables, which have the same law, but in addition converges nicely. So it can be stated in the following way. You have a sequence of probability measures, for instance, the sequence on the previous slides, which are laws. They are probability measures on a Polish space. This is why I said that it's important to have a Polish space as data space, and assume that the sequence is tight, which is nothing other as weakly precompact. Tight can be written in this way. So for each epsilon small, it means that actually the measures are sitting on some compact set modulo some set of small measure. So for each epsilon, there exists a big, maybe compact set such that the measure of the rest is less than epsilon for all n's. If you have such a sequence of measures, in particular, if they converge in the narrow sense, then you can show by what is called Prokhorov theorem that they are tight. Then there is a subsequence, and you can find random variables now. Before we had only sequence of measures, but now you have real random variables. They are sitting on a new probability space. The probability space can be taken conveniently as what is called standard probability space, which means that the space omega tilde is this interval 0, 1. B is just a set of Borel measures, and dy is just the Lebesgue measure. Now, the new sequence has the property that the law, the distribution of this new sequence equals to the original laws. So at the level of statistical distribution, the new sequence is exactly the same. But now what you recover is that actually this sequence can be constructed. I mean, what Skorokhod representation theorem tells you is that this sequence d tilde converges in the space X for every y, not only almost every y, but for every y. And so you are in the situation number one. You have a sequence of probability measures, you have the sequence of random data, which converges for every y. And so you take the corresponding solutions. They will converge according to this to the statement one, and since the law is equivalent, the law in the original space, which is the same, will converge as well. Okay, so that's exactly what is written down here. The Skorokhod theorem tells you that you can represent the original sequence by the new law. You get convergence in the new probability space, and since the laws are the same, you will get that actually the solution the law corresponding to the solution converges narrowly to some law of another solution. So you will get convergence in probability, or if you want, convergence in the weak sense. And for that, we need nothing else than Skorokhod theorem plus our statement about stability of strong solutions. Now let me make it more complicated. Since the convergence before is always on this maximal time interval, and we would like to get rid of this maximal time interval, in particular in numerical applications. If you want to apply, for instance, the Monte Carlo method, it's good to have solutions that are defined up to some interval which is deterministic, not t max, which is a random value, but a t which is deterministic. In order to get this, I will have to assume something more. I will have to assume that my sequence of solutions is bounded in probability. So what this means? I take a sequence of the data again, and I assume the data converges almost surely. So I have the same situation as on the picture number, or in the example number 1. But in addition, I assume that actually my data, my sequence, my solutions that emanate from this sequence is actually bounded. I mean, it's reminiscent, and of course, it refers to this to the conditional regularity criterion where I needed the solutions to be bounded. But here, I do not want to assume that the sequence of solutions corresponding to this data is bounded. I just want to assume something much weaker. I will assume that the sequence is bounded in probability, which is exactly what is written down here. So the sequence itself may not be bounded, but the part which is like big has a very low probability, which means that for each small epsilon, I find m maybe big, such that the probability that the norm of the solution is bigger than this m in this maximal norm is less than epsilon. And under this assumption, which is of course something you cannot prove for a given sequence, or at least for the sequence of solutions to my problem, it's extremely difficult to prove. On the other hand, it's not difficult for people to believe that it is true, because even, especially in numerical analysis, people always assume that solutions are bounded. I mean, so in the future, they will be solutions of a numerical scheme. So they always, I mean, that's a usual assumption in numerical analysis, that solutions are bounded. Here, we even assume something less. We just assume that with a very high probability, the solution is bounded, not necessarily surely, right? And surprisingly now, the conclusion will be, and for making this conclusion, we will use an analysis, will be that in this case, if I assume in addition this hypothesis of boundedness in probability, that actually the corresponding solutions of this data will converge to the solution D in xt on the same time interval here in probability. In particular, the limit solution will be defined on the whole interval 0 capital T, and the convergence will be in probability, which means again in the jargon of the theory of probability, in probability means in measure in the normal vocabulary of analysis. How do you show that? Well, the proof can be done in the following way. Again, you pass to the Skorokhod representation theorem. But now the goal is, I mean, because you would like to get a sequence of data which converges, but not only that the sequence converges almost surely, but you would like to convert your statement about boundedness and probability to the statement that your solutions are bounded pointwise, because in that case you can use the statement about regularity of bounded solutions. And this can be done in the way that you take the function lambda n, which is a supremum of, I mean, it's a supremum norm of the solution for the data dn, and you take it in the Skorokhod theorem as one part of your random variable. Passing to using Skorokhod theorem, you can convert everything to a sequence of, again, data, which has the same law, but also with the function lambda tilde n, and now this lambda tilde n converge to some lambda tilde, because that's the statement of Skorokhod. But if it converges, it means, and it converges surely, but in particular, since it converges, it must be bounded. And so you get a bounded sequence of solutions. And so now we know that this bounded sequence of solutions, for this bounded sequence, you have conditional regularity estimates, which means that your solutions are more regular on the whole interval 0t, and you can pass to the limit to the in this sequence surely, but on the whole interval t, and you will converge to a solution which corresponds to the limit emanating from the data d tilde. So you have convergence on the whole time interval. There is one little drawback now, is that actually this interval, this solution, they live on some equivalent probability space. If you do numerical analysis, you do not want to to see that your solutions are defined on the different probability space. You want to see solutions that you are computing on the original space. The way out is, fortunately, the fact that the solution is actually unique, because we have solutions which are determined by the initial data, and they are strong solutions, so they are unique. And if the limit is unique, we can use the so-called Jensch-Kirillov theorem. I will not spend too much time on explaining the meaning. It basically tells you that if the limit on the previous page was unique, which is, then you can pass to the original space and you can get convergence in probability on the original space. So, so far so good. Let me finish my talk by considering now the real approximate solutions. So now so far I have been working with exact solutions. I assume that they are bounded in probability and so on. Now I will consider approximate solutions, which I denote by H, where H is some kind of discretization parameter. So I take my data, and instead of taking exact solution of my problem, I take some approximation. This approximation can be numerical approximation, can be whatever. It must have the property that I will specify on the next slide, which says that actually this approximation is consistent. I will tell you what exactly I mean by that. So now I take a sequence of approximate solutions. So UH for each H is approximate, and the only thing I assume about this operator, which to each data D assigns the approximate solution, is that it's a Borel measurable function, which acts Borel measurable with respect to these topologies. This L1 space is not really necessary, just convenience, and the topology on the data space is given by the matrix I have shown you before. So I assume that I can construct these approximate solutions, and what is more, I assume that these solutions, I assume that I have a sequence of these approximate solutions, and that they are consistent with the problem. This is again terminology coming from numerical analysis. So now you can really think that you are having a sequence of numerical solutions, and consistency means the following. So rho n, un, and theta n are just approximate solutions defined by the operator on the previous slide. And what I assume is that they satisfy the equations. I mean, now all equations must be understood in the weak sense, and they satisfy the equation modulo some error. So they satisfy the first equation, and on the right-hand side, there is some error then E1, which is called consistency error in numerics. So as I said, the equation should be understood in the sense of distributions. The momentum equation is satisfied modulo some error. The entropy actually is replaced by inequality for some technical reason, which is also satisfied by some error, and the energy, which is now, because I consider for simplicity this kind of boundary conditions, is a non-increasing function, and I also assume that there is some error in the energy inequality, in the total energy inequality. And I say that my approximation is consistent if all these errors go to zero. In the weak sense, which means that for each test function phi, these errors will go to zero. So this is a property which is usually satisfied by kind of reasonable numerical scheme. And the statement that the approximation is consistent in numerical analysis means that you have consistent numerical approximation, while the last statement about boundedness of the energy is sometimes termed stability of the numerical method. So these conditions are in particular satisfied by a finite volume method we design modulo certain extra conditions that I would not like to discuss now. Now I would like to say that, well, this sequence converges again in some sense to the limit, but the limit should be a random solution of the Navier-Stokes Fourier system. And so there are several steps, and so I will explain it briefly how the whole proof works now. So I assume again that I have strong convergence of the data. So I take now again a sequence of data which converges to some limit P almost surely on the original probability space. I make again the hypothesis of boundedness of in probability that, as I said, it's quite natural in the context of numerical analysis. I mean, people always assume that solutions of numerical schemes are bounded. Now we assume something less. We assume that only they are bounded, or the unbounded part has very low probability. So I again assume that my sequence is bounded in probability, and I assume that I have a consistent approximation. So these are my assumptions. And under these three assumptions, let me point out, I do not assume a priori anything about the existence of the smooth solution for the limit problem. These are my only assumptions I make on my numerical approximation or whatever approximation. The statement is that, the statement is that the solutions converge almost surely or in probability to the exact solution of the Navier-Stokes system, to the exact statistical solution. Okay, so how does it work? First, I apply the Skorokhod theorem again to the sequence of these approximate solutions, again with the choice of the function lambda, which is just a supremum norm. I obtain a new sequence of data as in the previous steps, which has the same load, it has the same distribution as my original data, but it converges now strongly and surely with respect to the new probability space. And in addition, this lambda n, which is the associated supremum norm to this data, now converges also to some limit. In particular, it is bounded. So the conclusion I can make at this stage, since I do not know that these are exact solutions, so I don't have any a priori bounds, but the conclusion I can make is that actually these new solutions, the equivalent solutions in law, approximate solutions, converge up to a subsequence weakly to some limits in these spaces, because I have this bound, so I have this limit. And the convergence takes place surely in the new probability space. So for the time being, I obtain some weak limit, which is an L infinity function. I have no idea what this limit, what kind of equation this limit may satisfy. Of course, the dream is to show that the limit actually satisfies the Navier-Stokes system, which must be done again by using some kind of analysis now. First of all, this limit, you can show that it's a very general solution of my problem, which is called sometimes measure value solution. Again, I do not have time to go into details. Measure value solution is basically solution which satisfies the equations where the nonlinearities are interpreted as Young measures. And it is relatively easy to show, since we have weak convergence in an infinity of these approximate solutions, that the limit is a measure value solution. It's almost straightforward. This measure value solution we introduced some while ago in this paper, also in the context of problems with inhomogeneous temperature boundary conditions. This was generalized by my former PhD student Nilasis Chaudhuri in 2022. So now what we know is that the limit rho tilde, theta tilde, u tilde is not only whatever, but it's a measure value solution. Now mathematics come. We can show for the measure value solutions, although they are very general, they satisfy the weak strong uniqueness principle, which means that if the problem happens to have a nice solution, then the measure value solution must be the same. And so we know, since the data are regular, that my limit problem has a nice solution, at least on some maximal time interval. So on this maximal time interval, the limit must coincide with this nice solution. And there is no need for subsequence because the limit solution is unique. However, since the solutions are bounded in an infinity, the limit is also bounded in an infinity. So it means that my nice solution is actually defined up to the time capital T because it's bounded in an infinity. And so you get, I get convergence on the whole interval. And as a byproduct, I can also show that the convergence is stroke in LQ. And so I have almost my dream satisfied, which means I get convergence, but on an equivalent probability space given to me by the Skorokhod representation theorem, the last step is to pass to the original space applying the Jones-Krylov. And so the conclusion is that actually my solutions converge to the exact solution of the problem on the whole time interval strongly in LQ in probability with respect to the probability space. And so let me remind you that the only assumption I made was strong convergence of the initial data and boundedness in probability. So I think this is a nice demonstration that there could be some synergy between analysis and numerics. And I think by that statement, I will finish my talk. Thank you for your attention.
Thank you very much, Professor Eduard. So now we open the turn for questions and comments. So if anyone has some question, please open your microphone, type your question in the chat. Or so, is there any question?
Okay, good afternoon.
Okay, go ahead, Professor.
Yeah.
I would like to ask some question.
Yes,
go ahead.
Okay, my question is, I would like to know about the application in the industrial energy, industrial. For example, when I have free energy, the minimum free energy, I would like to know how is the implication in the production. Some elements, for example, for the production of the water. In the water industrial, I have some energetic equation, free energy, for example. And I would like to know what application have these results.
What application? I mean, these are equations of fluid mechanics, right? So you might be familiar with problems in turbulence theory. So an iconic example is the so-called Bénard problem. If you have two plates and you heat them up, of course, it's simplified, but you can see about something specific, like in, for instance, in geophysics, thinking about some fluid which is being heated and maybe even rotating. So you have two plates. Each of them is heated each of them at different temperature. And between these two plates, you can see the motion. If the difference between the temperatures is very high, the motions becomes turbulent. So that's one of the applications. I mean, another one is really is Taylor-Kuet flow, where you can see two relatively moving objects that would. So it's a compressible Navier-Stokes. So this is, these models, these model situations, meteorology, in astrophysics, in particular, the dynamics of gas stars. It models turbulence in air or in gases. There are, I would say, many applications.
Okay.
So Eduard.
Thank you. Anything again?
Can I
I mean, of course, it's simple, right? I mean, you might imagine that you take into account, for instance, speaking about stars, it makes sense to include also the effect of magnetic fields, which what we are trying to do right now. But these are really problems that occur in applications. This is a fluid mechanics, and that's a full system. There is nothing is neglected.
So can I?
Yes.
Yeah.
Eduard, Vladimir. Eduard, you do not have even the deterministic case that the stability, usual stability, that if the initial data are closed, two initial data are closed in some topology, then the solution should be closed. So you do not have this.
This is here. I mean, it's not exactly what you say, but it's exactly the stability statement, right? This means that if you are close, meaning if you converge, then the solution converges. So if the data are close, the solution is closed. But the conversion takes place only on the maximal time interval, because the limit solution may not be defined forever.
Yes, well, because I'd like to say that if you do not know exactly the data, so you like to work with this uncertainty, but we already know that these two close initial data should converge. I mean, and not should converge, should implies that the solution should be close. Somehow, with this your technique to take the initial data with probability space, somehow
you just, yeah, I mean, but that's trivial. This is the statement here, which is written here, basically.
Okay, okay, it could be a trivial question, but somehow if you know that the two data are close, what's the main motivation to perturb the initial data with a probability parameter?
Because in certain cases you may not know the data exactly. You may have only some not really exact situation, in particular if you collect the data from some observations like in meteorology or whatever. I mean, speaking about gases on
Sure.
in stars, of course you don't know exactly what the temperature is. You just may
Like
guess
should
that
be
it's in
close to
certain
the-
range, right? And it's also known that even if the data are exact, you get better results if you take some kind of statistical approximation, like in the Monte Carlo method, that you can actually compute the expectation rather than exact values. And it makes the computations like I mean the schemes converge better in this case, right? So it can be also useful from this point of view. Of course, this problem is not stable globally. I mean, since we have non-trivial data, we don't have. I mean, we don't have something like stable equilibrium solution or things like that.
Okay. Okay. Thank you.
So another question. Oh yes, please, Enrique.
Thank you for your talk. I have a question. If I have understood well, you didn't change the right-hand side. I mean, you didn't consider this was a moving data.
Sorry.
G,
Yes.
the right-hand side.
Oh, you want to have a random G? Okay, I can consider random G if you wish. Yes.
But the results are the same.
Yeah, I would say we will get the same result. You know, what I don't like is when people impose a function which is not like gradient, because there is thousands of papers concerning driven Navier-Stokes with G on the right-hand side, which is not a gradient. But if you think about it from the physics point of view, the only force that can be there is the gravitation, or if you want magnetic force, whatever, but then you need magnetic field. So normally this G, the action of the external, I would say, external forcing should be expressed through the boundary condition. This is our philosophy in this approach, is that we really want to have a real fluid. So everything is driven by boundary conditions, not by some G on the right-hand side.
Yeah, I understand this viewpoint. I understand this viewpoint, but well, I am going to speak about something that is different. If you adopt a viewpoint of control, then you must G to be anything. So,
but the control should be in the boundary condition, not in G. What you will control by gravitation? How can you control gravitation?
Well, you can move. You can move.
Yes, you can move it. Yeah, I agree. You can move it, then you will get something. Yeah, sure. Sorry.
So it's not so natural as the boundary condition viewed as the control, but you can move. So
yeah, but I would rather see to control the velocity on the boundary, or the temperature, or whatever. Not really G. Of course, you can imagine that you have a container and you are moving it. Yeah, that's true. Then this would produce, if you move to the non-moving frame, this can produce some right-hand side. Sorry, that's true. Yeah.
Okay. Thank you.
Okay, is there any other question or comment? If no, let us thanks again, Professor Eduard Feireisl. Thank you very much
for the invitation.
This wonderful talk. So I give the word to Professor Mauro to end the session.
Maybe I just stop sharing.
The next section will be